Okay.
So, welcome everyone to the Motwani Distinguished Theory Colloquium. This is an ongoing series of theory colloquia where sort of the world leaders in theoretical computer science come and give talks aimed at a relatively broad audience. The series is named in honor of our late colleague, Rajiv Motwani, who was a member of the Stanford faculty, the CS department, from 1988 until 2009. And as you probably know, he contributed many fundamental and influential results in theoretical computer science, ranging from the PCP theorem to locality-sensitive hashing, and that was in conjunction with our speaker today, and many, many famous results in randomized algorithms. And this colloquium series is made possible by a generous gift from the Motwani Judea Family Foundation. So I'm honored to introduce our speaker for today, Piotr Indyk. Piotr is one of our own, so he got his PhD from the Stanford Computer Science Department in 2000, advised by Rajiv Motwani. And ever since then, ever since 2000, he's been a professor at MIT, where he is to this day. Among many other awards, let me just mention one, which was the Paris Kanellakis Award. This is the Theory and Practice Award given out by the ACM, really sort of major national award. That was for his work on locality-sensitive hashing that he did here at Stanford with Rajiv. And incidentally, actually, our own Moses Charkar also co-shared that award. So since then, he's continued to make major breakthroughs on lots of different problems, ranging from compressive sensing to a sparse version of the fast Fourier transform. And so today he'll be speaking about some of his latest breakthroughs that illuminate the barriers to faster algorithms for lots of different problems, including some that you probably studied in your own intro algorithms class, like CS161, like edit distance, indicating why we can't seem to have faster than quadratic-time algorithms. So let's welcome Piotr.
Thank you. Thanks, Tim. It's an honor to speak in the Rajiv Motwani series. Can you hear me well? All right. So in this talk, I want to give you an overview of research that several people, including myself, did over the last few years, which aims at establishing limitations of algorithmic performance for some of the most fundamental algorithmic problems used in big data processing. And by several people, I mean, let's see. Okay, Artur's batch course, with whom all of this material in this talk has been co-authored. And Artur's also created most of the slides in this talk, so double thanks to him. And the last part of this talk is also from a joint paper with Ludwig Schmidt, who's also my student. All right, so what this talk is about? Well, the starting point of this talk is that we are living in very interesting times for many reasons, but here I'll be just talking about the algorithmic perspective, right? So from algorithmic perspective, lots of interesting things are happening because there are several long-standing trends which either are hitting a wall or are colliding with each other, right? So what do I mean by that? Well, on the one hand, the amount of data that is being processed, generated, is growing, right? It's a trend that has been around for a while, and it doesn't seem like it will stop anytime soon, right? So the input gets larger and larger, but at the same time, our capability to process it encounters certain difficulties, right? So the Moore's law, which was for many decades was a guarantee of speed ups every few years, right? Now, apparently, maybe it's not hitting the wall, but let's just say it's encountering difficulties, right? And so here what you see on this plot is the latest ITRS roadmap, which tries to predict the size of the gate as a function of time, right? And for many years it was shrinking, but now the prediction is that it might stop shrinking in the foreseeable future. Right, so the combination of these two trends leads to some very interesting results, right? Because on the one hand, input is growing, but our capability of actually processing it, at least using general purpose computing, might just encounter the wall. So the combination of these two trends leads to some interesting developments, which are perhaps best summarized by this wonderful tweet. I don't know if you guys can see it from far away. I'm just going to read it. An engineer from Google told me today that he had a hard time finding available machines for production because of the NIPS deadline. Okay, so NIPS is one of the two main machine learning conferences. And I mean, it's not an accident that this tweet happened in the concept of machine learning, because machine learning is one of the places exactly at the intersection of these two trends. Right? Because on the one hand, using more data leads to much better results, but at the same time, I mean, many of these algorithms for neural networks and deep learning and so on, you know, they can take days or weeks to complete. Okay, so what can we do about it? Well, this is certainly not news, right? I mean, this is something that has been known for a while. And there are several different ways of trying to overcome this difficulty. One of them is to design better hardware, more specialized hardware, right, which is tailored to particular computational tasks, like for graphics or for learning or other specific applications. And that's, of course, one of the major directions. Another task, you know, something closer to my heart and many people here, is to develop faster algorithms, right, for some of the key problems in those areas, right? And you know, of course, this is something that people have been working for many decades, and there are many success stories, right? You know, for many basic problems, we can now have algorithms which are much faster than previously known, and this is particularly true if we use, say, approximation and randomization, right? Like using these two extra tricks, good things can happen. But in this talk, I would like to focus on the complement of these two directions, which is to try to understand what are the limits, right, to further algorithmic improvement on some of the basic problems. Okay? And you know, in a way, such limits already exist in the hardware world, right? Because we have physics. So, for example, we know that if the transistors shrink below certain diameter, right, that at some point we start encountering quantum effects, right? And this causes a problem, right? Or, you know, also from physics, we know that if the clock speed starts to increase, you know, that generates lots of energy, which needs to be dissipated, right? So again, it's a problem. So, you know, we know quite a lot about limitations of hardware, but we don't know as much about limitations of algorithms, right? So it would be very nice to have similarly quantitative predictive tools that helps us predict what is the best thing that we can know from the algorithmic perspective. And there are multiple reasons why we would like to do that. One of them is just purely scientific, right? It's a fundamental problem, it's a basic problem, it's a fascinating problem, right? So we'd like to understand it better. But there is another equally important aspect, which is that if we understand what the limits are, it can actually help us design better algorithms. Right, because you know, as many of you know, the life of the algorithm designer often looks more or less like this, right? There is a limited time, but there are several problems to work on, and even for the same problem, there are several different formulations, right? That formulations or variant and so on that you can explore. Right, and which one to choose? I mean, you can use your intuition, you can use heuristics and so on, but at the end time, you know, we all make mistakes, right? And lots of effort is just wasted. Okay, so it would be much nicer if we had some sort of science or a roadmap that would tell us that, okay, these variants most likely are not going to lead to anything, you know, to any algorithmic solutions, right? And instead, you know, this lets you explore options which potentially might be feasible. Right? And of course, you know, in the algorithm design, there are, in several aspects of algorithm design, there are already tools which let us develop such limitations, right? So for example, for sublinear time or space algorithms or communication protocols, algorithmic game theory, right? We have communication complexity, which helps us get pretty good quantitative lower bounds. Right, and actually they are pretty tight. So in many situations you can get tight results. And similarly for approximation algorithms, right? Like if you want to figure out what is the base approximation factor, I mean, there's a PCP theorem, right, which tells you what are the thresholds, right? What can be, that below certain level you cannot do certain things, right? But from the perspective of the algorithm design, especially in this low polynomial regime, until very recently we did not have such tools, right? So life looked more along these lines. Right, that there were many options, but not necessarily that many hard quantitative guidelines of what is the best thing possible. Okay. So this talk will cover some of the recent developments aiming towards obtaining such guidelines. All right. Now, of course, there is already a methodology which helps us with certain class of problems, and it's based on the well-known P versus NP conjecture, right? So I guess all of you, or most of you here know what it is, but just to summarize, right, the basic idea behind this methodology is summarized by the quote from Gary and Johnson, right, which says that I cannot find an efficient algorithm, but neither can all these famous people. Right, so this is essentially a way of a lower bound by, blaming others, so to speak, right? And basically what it means is that, okay, if you prove that the problem is NP-complete, right, then of course, it might be the case that you can solve it for a specific instances, right? You can use the properties of the input to get a better solution, or maybe you can come up with the approximate solution. Of course, in principle, it could be also the case that you get a general algorithm, right? P could be equal to NP after all. But in this case, this would be a major thing, right? Sky would fall, crypto systems will be broken, and so on, right? So there would be bigger issues to worry about, right? So this is a very good excuse or explanation, depending how you look at it, for which establish limitations of what we can do. But in the context of big data, it does encounter difficulties, mostly because it equates the notion of efficient with the notion of polynomial, right? And in many situations like crypto, it makes perfect sense, right? But once you start looking at the big data, then it doesn't quite match what we mean by efficient, because if you look at the problem which has a quadratic-time solution, right? Quadratic-time is pretty efficient. It's a pretty low polynomial. But once you run this algorithm on, say, gigabytes size of data, it can run hundreds or even 1,000 years. Okay? So in order to apply this methodology to big data problems, you really need to refocus from polynomial to something much lower in the complexity range, and for example, linear time, right? Or near linear time. Okay? Okay, so fair enough. So this something can be done, but then again, if we try to do it, then we encounter the second difficulty, which is that P versus NP actually does not distinguish, right, between, say, algorithms which run in n time or n squared time or n200, right? Like all of these things are collapsed together. Which means that, from what we are doing, we are taking very different complexity classes, right? But we are putting them into one big equivalence set, okay? So we need to be able to distinguish somehow between these different classes. And in order to do that, we need two things. We need conjectures which are stronger than P versus NP, right? Because using stronger conjectures, we can get stronger implications, right? And at the same time, we need new reduction techniques, which are more efficient than polynomial, right? So that we can transfer the complexity classes. All right, so there are several such candidate stronger assumptions, and one of them, quite popular, is a strong exponential time hypothesis. Out of curiosity, how many of you have heard about that? Okay. So I think I'm preaching to the choir, so to speak. Well, nevertheless, let me explain very quickly what it is. It addresses the complexity of the SAT problem, right? Given the formula, you want to satisfy it or find a satisfying assumption. And what it says is that this problem cannot be solved in time, which is better than 2 to some constant slightly smaller than 1 times n. Okay, times some extra polynomial time. Okay, so just for the background, okay, an algorithm with a running time of the form to the n is trivial, right? Just enumerate all possibilities and verify them. So what this conjecture assumes is that you cannot improve this algorithm even just slightly, right, in the sense of the exponent. And that's also, you can see that's a much stronger assumption than P not equal to NP, because P not equal to NP only postulates that this problem cannot be solved in polynomial time. Okay? In contrast, here you go from polynomial to exponential, right? So we are raising the threshold considerably. So it's a much stronger assumption, but it also helps us get much stronger results. Okay, and because of that, several people, I think Scott Aronson in particular, refers to it as a P not equal to NP on steroids, right, for rather clear reasons. All right, so what is known about this hypothesis or conjecture? Well, first of all, it's a natural conjecture to make. Okay, because people have been working on fast algorithms for satisfiability for many years, right? So in particular, the well-known procedure, Davis-Putnam procedure for finding satisfying assignments, I mean, it was published in 1960, right? So people were working hard on this problem, and actually there has been lots of progress, right? So in many areas like model checking or other applied domains, people are able to solve very large SAT instances. Right, so there has been lots of progress, but in many other areas, such as, for example, cryptography, I mean, the progress was much more limited, right? I mean, there hasn't been really much application of SAT solvers to breaking crypto systems. I mean, there were some, but certainly, you know, not to the level of what happens in model checking. And certainly, there are no better algorithms which work in sub-exponential time, in the sense of this conjecture, for general inputs. Right, so that means that there has been lots of progress, right? It's not a problem that people haven't been studying, right? There has been lots of effort, and there has been lots of progress in certain domains, but still we don't have any better algorithms, right? So it's a natural conjecture to make. It's consistent with the state of art, and lots of people explicitly or implicitly worked on disproving it. Now, that said, it's a very strong conjecture. So many people believe it's true. Many other people believe it's not true. One example of said denialist, right, so to speak, is Ryan. Yeah, so I don't think anybody made any polls, right? But according to Ryan, set is false is a minority opinion, right? So, I mean, you know, you can, the opinions about this conjecture can vary, but whatever you might think about this conjecture is still a very useful tool for proving limitations of the algorithms, right? You know, depending on how you interpret those results, you can think about it as a, ultimate impossibility result, right? Or you can just think it about, just a sign that maybe you can make a progress, but in order to do that, you have to overcome quite a few obstacles, right? In either case, it's a natural way of formulating and proving limitations to the algorithms. And because of that, there has been lots of work in this area over the last few years. I will not manage to mention all of this work, but I can mention the people who developed most of these results. So Amir, who's there, and Virginia, who I don't think is here. Yeah, so both of them developed lots of wonderful results in this area, and I think that Amir had a defense on Tuesday, right? So if you want to learn more about it, read his thesis when it will be actually written, right? So hopefully this will motivate you to actually finish it soon, right? So, all right, good. So this is the background for this talk, okay? And now the topics that specific topics that I will cover are 4 or 3 results which show either quadratic or rectangular lower bounds for a bunch of basic problems in data processing. So in particular, I will focus on problems such as edit distance, right? So it's a basic problem. It lets you compute the dissimilarity between 2 sequences with many applications. Regular expression matching, right? So again, very popular task. And I will also look at 2 problems in machine learning, namely kernel support vector machines and the problem of computing gradient in neural networks. Okay, and for all of these problems, I will show either quadratic or rectangular lower bounds. Okay. All right, so edit distance. So let's start from it. Edit distance is also known as the Leverstein distance. It's a basic way of computing the dissimilarity between two sequences, and it has a very natural definition. It's a number of basic operations needed to transform one sequence into the other. Okay, so let me give you a timely example. Okay, so one of the applications is to try to figure out what our president is actually tweeting about, right? And if you want to compute the distance between these two sequences, like you can see that it's actually 4, right? Because you just have to insert e, right? And then you just do character substitutions. Okay. So that's a very useful notion. It has many applications in computational biology. So we would like to understand how efficiently can we solve it. So what is known about the complexity of this problem? Well, it's a prototypical example of a problem which has a very efficient solution using dynamic programming, right? So the first result of this type was published in '74 by Wagner Fischer, and they show that using this dynamic programming approach, if you build a table, you just n by n table, if you perform the computation, you can find the solution, both the actual distance as well as the appropriate alignment in a quadratic time. Okay, so that's a very useful, very widely used algorithm. It turns out to be not optimal. In fact, a few years later, it was improved by logarithmic factor, which is not that much, but it's an important step. And in fact, it can be improved even further by another logarithmic factor if you assume that your alphabet size is constant. Okay, so you can improve this by 2 logarithmic factors, but this is really it. Right? So really, the best algorithmic solutions run in essentially quadratic time. Now, that holds for the general case, and there is a whole army of algorithms which works for either approximate case or some special cases like bounded distance and so on, right? But for the for the general problem, the best known algorithm had a quadratic running time. So in this talk, I will give an overview of a result, which can be viewed as an explanation for the state of art. I will show that there is no sub-quadratic time algorithm for this problem unless set fails. Okay. So this provides somewhat of an explanation why no better algorithm has been discovered. All right. Any questions so far? All right. Okay, so how are we going to show this result? Well, not surprisingly, we'll reduce sampling to sampling, right? But the good news is that because of the prior work on this problem, we actually don't have to start from scratch. And instead of reducing from the satisfiability, we can start from a different problem, right? Which is actually much easier to handle. So in particular, we're going to start from the orthogonal vectors problem. How many people have seen this problem before? Okay. Yeah, the theory group is very well represented, right? So, okay, good. So this is a very natural problem, right? You are given 2 sets of vectors in some d-dimensional space. The vectors are binary, right? And what you want to see if there is a pair of vector from one set and another vector from another set, which are orthogonal to each other. Right? Since these vectors are binary, they are orthogonal if and only if the ones of 2 vectors do not overlap. Right? If there's any overlap, then they are not orthogonal. Right? It's a very natural problem. It's closely related to so-called partial match problem. And what can be said about the complexity? Well, it's trivially solvable in quadratic time, right? Because we can just enumerate all possibilities. In fact, there is a faster way of solving this problem if the dimension of the vectors is logarithmic or order of logarithmic. But already when you say take your dimension to be log square n, even at this point, the best algorithm is pretty much quadratic time, right? So it's natural to assume that this problem cannot be solved in better than quadratic time, and that's what the orthogonal vectors conjecture says, right? That you cannot do it in sub-quadratic time. And supporting evidence for this conjecture is that Ryan Williams in 2004 showed that, in fact, orthogonal vectors conjecture is implied by set. right? That means that for our purpose, we don't have to start from satisfiability. We can just take orthogonal vectors and reduce it to the eddy distance, and then we'll be done. All right, so in the next 10 minutes or so, let me give you an overview of how this can be done. So first of all, we're actually going to reduce orthogonal vectors to a slightly different problem. Instead of in this new problem, instead of trying to compute the distance from the x to y, we'll try to find the distance from x to the best substring of y. Right? So this is a pattern matching. When you have a pattern, you want to find inside the text, right? And you want to minimize the number of errors. Right, so this is the problem that we are going to focus on, and actually it turns out that this is without loss of generality, because for our purposes, these two problems are actually equivalent. Okay? So how does the reduction work? All right, so as all reductions, you take the input to one problem, and you generate the input to the other problem. Right, so you take your sets, and you map each set to a sequence, right? A to sequence X, B to sequence Y. And this mapping has to satisfy two constraints, right? If the sets actually do contain orthogonal pair, then after the mapping, the pattern X occurs in Y with few errors. And otherwise, any way you try to match X in Y, you are going to have quite a lot of errors, okay? And of course, what we want is we want the construction time to be linear, right, so that we can transfer the complexities of the problems to each other. And if we show a reduction like that, then we prove this theorem, right, that if pattern matching can be computed in sub-quadratic time, then orthogonal vectors also can be computed in sub-quadratic time. Therefore, the conjecture is false, and therefore the set is false, right? So we prove our theorem. All right, so how can we do that? Well, there are two steps in the argument, in the reduction. In the first step, we assume that certain vector gadgets exist, and assuming those, we are going to prove and demonstrate the reduction. Okay? And the second part, of course, is to actually construct those gadgets. Now, in this talk, I will focus on the first part. The second part is a little bit more ugly, so if you have any questions, you can ask me offline, right? Or in the worst case, you can just, read the paper, right? If other options don't exist. Okay, so let's see what's the idea behind the reduction, assuming that we have a vector gadget. So what is the vector gadget? What do we want from it? Well, a vector gadget is defined for a vector in each set, right? So for vectors in the set A, we generated sequences alpha. For vectors in set B, generate sequences beta. And what we want is the following property. If A and B are actually orthogonal, then the eddy distance between the gadget is small. So now we're talking about the eddy distance, right? Not the pattern distance, but the eddy distance. And on the other hand, if these two vectors are not orthogonal, then the eddy distance is equal to L, where L is supposed to be large. Right? So L large, S small. And I should mention that this equality here is pretty crucial, right? I mean, there are many situations that you can live with, in one case you have less than, in the other case you have greater than. But in this particular case, it's crucial that this equality here is tight, right? So we want, the vectors are not orthogonal. You want the distance to be always equal to the same value, and it has to be larger than S, okay? So suppose that we have such a construction. Then the rest of the argument is actually fairly natural, because we can do the following thing, okay? So how do we construct the sequences that we used for the pattern eddy distance? Well, we take all the gadgets and concatenate them together. Between the gadgets, we put special characters, right? Actually, there is not just one character, but there is a large number of these characters. Right? The idea is that gadgets should not interact, right? So we just put lots of separation there. Now, I'm going to remove them from the picture, right, so that things are more clear, but just keep in mind that there is some separation in between. All right, so we do it for the sequence X. We do something pretty similar to the sequence Y. It's just that we are padding the sequence with extra gadgets T, and these are the vector gadgets for a vector which are all ones. Okay, so all ones vector is pretty harmless, right? Because it's orthogonal. It's not orthogonal to any non-zero vector, right? And we can just check if there are any zero vectors, right? So we can assume they are not there, which means that adding these guys doesn't change anything. Okay, so we just put these guys, and now we are pretty much done. Okay, so what we need to show is we need to consider two cases: either there is an orthogonal pair or there isn't. Okay, and here is a cheat sheet of what we want from our gadgets, vector gadgets. Okay, so suppose that there actually exists an orthogonal pair, right? And for the sake of concreteness, let's assume it's A3 and B1. Okay, then we have to show that the distance between this and this, in the pattern matching sense, is small. Okay, and not surprisingly, we do it by matching alpha 3 to beta 1, right? And we know that since the original guys were orthogonal, the distance is small, right? So the distance or the cost incurred by this particular match is only s. And then we can take this match and just extend it in both directions, okay? In each step, we are matching two vector gadgets, right? And this can cost us S or L. We actually don't know that, right? Because there could be more orthogonal pairs. But we definitely know that each of these costs us at most L, right? Which means that at the end of the day, we get distance, which is at most S plus N minus 1L, okay? And this is going to be our definition of small. Right, so we saved one character or one part of the cost, right? We know that it's S, okay? All right. So now we have to complement this argument, okay, and consider the no case where there is no orthogonal pair. And, we can roughly see what is happening, right? I mean, we can use any matching we want. And one can show that thanks to those separations, you always can assume that you match gadgets to gadgets, right? But no matter how we match these gadgets, right, we always incur a cost of n times L, right? Because there is no orthogonal pair, right? So by this definition, the gadgets are, the distance is L. So we can do it any way we want, okay? We always get n times L. And this means that we are pretty much done because n times L is greater than s plus n minus 1 times L, which means that we have a gap. Right, so we separated the S from no instances, which means that our reduction is correct. Right, so we are done. All right, are there any questions about it? No questions? All right. All right, so that's how you prove hardness of the edit distance. So let's now change gears and focus on the regular expression. Out of curiosity, how many of you have used a regular expression in your life? Okay, probably everyone, right? Yeah, it's a very powerful tool for searching in your text on some data sets. All right, so yeah, so there are several different languages in which you can express regular expression. In this talk, I will focus on languages which allow concatenation, or a star or plus, right? So star is a clean star, right? So just take whatever is there, whatever this argument, and this argument can repeat 0 or more times, right? So plus can repeat 1 or more times, okay? So you're given a regular expression, you are given a text, you want to check whether there is a substring in the text which matches the regular expression, okay? In this case, you do have a match here. All right, so what do we know about this problem? It can be solved in a rectangular time, right? Because you can just construct non-deterministic automaton for the regular expression and then just simulate it. So that's true for general cases, but well, again, as before, you can improve it, in this case, by roughly 1.5 logarithmic factors, right? But again, that's as much as it is known how to make this algorithm faster. However, at the same time, the situation is a little bit more complicated because there are many special cases of regular expression that actually support much faster algorithm, right? So, perhaps the classic one is the pattern matching, right, due to algorithm due to Knuth-Morris-Pratt, right? In this case, the regular expression is just a concatenation of symbols, right? And you can search for a pattern in the text in linear time. In fact, the same can be done if your regular expression is an OR of concatenations, right? So if you have a bunch of options, right, and you can choose either of them, this also can be solved in linear time. On the flip side, if you have a concatenation of ORs, right, you have several options, characters for each particular place, this also can be solved, not in linear, but in something like n log n time, right, by using fast Fourier transform. So the situation is kind of interesting, right? I mean, there is something for the general algorithms, but there's also special cases which support much faster solutions. Okay, so Arthurs, Bachkurs, and I wanted to understand it better. So we tried to investigate this problem in more depth. And actually, we investigate in pretty high depth. Okay, and this is what we got. You know, arguably, we went a little bit overboard, right? Was this? Well. At the end of the day, we managed to classify all the complexity of all different combinations of a regular expression depending on their type, right? So what's the type? You know, for example, this expression here is of type concatenation OR, right? Because this is a concatenation of ORs. Right, so we managed to classify the complexity of regular expression, matching, and also membership for all types of length 2 or 3. Okay, and you know, this was like one of those papers with 96 results, which was actually kind of interesting. Now, to be fair, most of these problems are actually not, I mean, some of them are plain stupid, right? Some of them have been studied before. You know, several of them are interesting. But perhaps the main message from this analysis is that we managed to get tight upper or lower bounds for all problems except for this one. Okay? So this is this so-called Wordbreak problem. And I'm going to focus on it in the next couple of slides. So what is the Wordbreak problem? We are given the text of some length and a collection of words. You can think about it as a dictionary. And what you want is to figure out whether the text can be decomposed into blocks where each block is one of the words. Right? The words can repeat, that's fine. Right? But you cannot have any extras. For example, if this is your text, which actually happens to be an actual word. Are there any German speakers in the room? Okay, so you know what it means, right? Kind of, yeah. Yeah, it's an actual German word. I believe it means insurance companies providing legal certificates or something like that. Exactly, right? So you would like to take this compound, known, and decompose it into basic components, right? And this is exactly the goal of this problem, okay? In this particular case, you know, this will be the solution, right? It's a compound known, which consists of 4 basic words. All right, so in general, this problem is a pretty common question asked in the interview, and you can Google Dan Tunkelang's blog, who has like a long story about it. It can be solved in n times m time, because after all, it's an example of a regular expression, membership problem. It's actually not very difficult to improve it to n times m to 1/2, right? So you can improve this exponent in m from 1 to 1/2. And this expression, I mean, it looks very nice, right? So we thought that this is actually optimal, and for a while we tried to prove it's optimal, right? But we failed, and then we switched sides, Okay, and turns out that in fact this expression is not optimal, and you can get improve this exponent from 1/2 to 0.44. Right now, this is not a great improvement, but it indicates definitely that this complexity was not optimal. And in fact, after our paper was published, Brinkman and Green-Larsen showed that one can improve this algorithm even further, and they reduce the exponent to 1/3. And in fact, they even showed some evidence that this 1/3 might be optimal, although the strength of this evidence is a little murky, right? So I'm not going to say exactly what it means. However, the bottom line is that thanks to the fact that we have this way to indicate that certain problems can be solved and that certain problems cannot be solved, most likely, or certain problems cannot be improved, it removed a bunch of possibilities, right, which let us focus on one problem that we actually didn't know how to solve, and it turns out that you can get actually non-trivial solutions, right? So one can view this story, right, as a demonstration of the power, right, of our limitations, right, which can let you focus on those problems for which we actually don't know of any limitations. All right. Any questions about that? All right. In the last part of this talk, let me focus on problems which occurred in machine learning, and particularly focus on two problems, Kernel SVM and gradient computation, right? So how many people have seen SVMs before? Okay, again, almost everybody. So very quickly, in SVMs, you are given a collection of points with the labels, and you want to come up with a hyperplane classifier, right, which let's say goes to the origin, although it's not a crucial assumption, and you want to divide the whole space in a way which is consistent with the labels. So now, of course, there are many such classifiers, so you want to find the best one, which in this case, the best one, which means that it maximizes the margin. Now, the problem with this basic approach is that for many situations, such a classifier doesn't exist, right? Because many data sets are not linearly separable. So the fix for this is a so-called kernel generalization, in which before you actually design this classifier, you take your points and you lift them to a much higher dimensional space, potentially infinitely dimensional space, right? And then you try to find this classifier. So that's what kernel SVM is. And at the end of the day, solving this problem boils down to solving this quadratic optimization problem, right? You have a quadratic form here, you have some linear constraints here, right? And you solve it using whatever methods you have. And one nice feature of this formulation is that it only involves this so-called kernel product, right? The kernel product is just a product between the lifted versions of the input vectors. Right, so you actually don't have to physically lift those points, right? Which is good because those dimension in the lifted space could be infinite, right? But instead you just have this oracle which tells you what the product is. All right, so how efficiently can you solve this problem? There are actually at least two different ways, which quite different performance. You could use interior point method. Okay, which is very accurate. You can solve it to very high accuracy, even for very tiny epsilon. The algorithm is very fast because the dependence on the epsilon is only logarithmic. Okay. On the other hand, the dependence on the number of points is at least quadratic. Right, and this is because the first thing that those algorithms do is they materialize explicitly this kernel matrix. Right, kernel matrix n by n, which means that here already you are paying n squared time. On the other hand, you can use a different set of tools, right? You can use a stochastic gradient descent, and those algorithms are actually very efficient in terms of n, but their dependence on epsilon is actually no longer logarithmic or even logarithmic, but polynomial, right? So you get something like 1 over epsilon or 1 over epsilon squared, depending on the tools that you use. Okay, it's a very interesting dichotomy between these two cases. All right, so that's SVM. Now the second problem that we're going to look at, the second machine learning problem we're going to look at is the batch version of the gradient computation. Okay, so how is this problem defined? Well, we are given a neural network. I mean, it's not a deep neural network, it just has 3 layers, right? The input layer, the hidden layer, and the output layer. Okay, and there are weights here, and nonlinearity S in the middle. And on top of that, you are also given a collection of examples with the labels. Okay, and what you want is you want to compute the gradient of the loss function, right, which is just a sum over all example of the loss, right, occurred by predicting one thing while the true label is potentially something else. Okay, so this is, again, one of the basic steps in many algorithms which compute the optimal, which optimize the neural network classifiers. What is known about the complexity? Well, there's a very well-known backpropagation algorithm which essentially computes this gradient example by example, right? And given one example, it computes all the gradients in linear time, right? Linear in the size of the network. But if you want to do it for the batch case, then you have to just repeat this computation example by example, right? So then the running time is multiplied by the number of examples, right? So this is the best thing known. All right, so what can be said about the limitations for these 2 problems? Well, for SVMs, we showed that assuming set, you can exclude an algorithm which will be the best of both worlds. Right, so you cannot get an algorithm which has a sub-quadratic dependence on n and say logarithmic dependence on 1 over epsilon. Right, in fact, the result is even stronger. Right, but it means that you cannot just combine the dependence on epsilon from the interior point and the dependence on n from the stochastic gradient descent. Right, you kind of have to choose. Okay. This is I'm not sure you can see it. This is the exact statement of the result, but let's just ignore it here. For the gradient computation neural networks, or more precise, the batch gradient computation, we show that if your activation functions are either sigmoid or RLU, which are the popular ones, then again you cannot do anything better than the rectangular time of the just a naive application of backprop, again assuming set. Okay, and this is true even if you want some very rough approximation to the norm of the gradient vector. Right, so really, even if you want, if you are okay with some very rough approximation, you still have to spend this amount of time. Okay. Now, interestingly, the fact that we are using either sigmoid or LU here is pretty crucial, because, for example, you could replace them by quadratic function, and then it's actually not difficult to observe that in this setting there is a faster algorithm which runs in this time. Right, now, of course, if you compare this time to this time, there are trade-offs depending on d, but in our case, d is polylog n, right, which means that this algorithm is actually always faster than this. Right, so this means that for different activation functions, you actually can get very meaningful differences in the behavior, which raises the hope that maybe there are activation functions which are interesting, right, from the practical perspective, but for which faster algorithms do exist. Right, now, unfortunately, quadratic activation functions are not very interesting in practice because they are very non-local. Right, unlike say sigmoid or LU, right, and people studied them, but they are just not, they don't work well. Right, so this is not a, it's not a practical algorithm, but it leaves open the possibility that by proper choice of the activation function, one will actually get a meaningfully faster algorithm. All right, any questions about these results? The d is log n square because, I mean, for the reduction, it's good, right? Because it means that d has to be only log n square. And it's log n square because we reduce it from the, for the problem, which is hard, or conjecture will be hard, even in the log square n dimension. Yeah. The lower bound applies to any algorithm well, I mean, if you assume, if you start from a conjecture which applies to randomized algorithms, which is the case, then yes, yeah. Yes?
So for example, suppose we have a class of examples,
Right.
which you can learn using signal function and get very low loss.
Right.
Very good prediction.
Right.
The lower ones,
Right. Well, so the lower bounds are for the general purpose algorithms, right? So, you know, like obviously, I mean, you know, for example, if all the inputs are 0, right, then I can compute the gradient much more efficiently, right? So, yeah, I mean, it's a worst case result, right?
one of these problems are the natural. One thing that often happens in industry is that people say that this particular corpus is easy to learn.
Right.
Or this particular edge distance, I believe, is going to be small.
Right.
Hence, I'm in my equity.
Right.
And the examples of lower bound, which has where algorithm will be slow, even for instances where either you can learn them, either when the deep learning algorithm will do very well, and the edge distance is known to be very small.
Right. Well, you know, first of all, if the edge distance is small, there are faster algorithms, right? So, but you can use that as a parameter, and then you can actually get still pretty good prediction, parameterized by the value of the distance. Yeah. But yes, I mean, you know, these results, actually not just this result, but in general, this type of results, right? I mean, they should not be viewed as an impossibility of solving any particular problem, but more as a limitation to a general purpose algorithm solving this problem, right? So it's I would say like once you view it, I mean, the implication is somewhat lesser, right? But it's still meaningful, right? I mean, backprop is, I mean, it's a general purpose algorithm, right? It runs always in a given time, right? At the distance, the same thing, right? So it means that if you want algorithms like that, you know, simple algorithms which always work, you don't have to worry about when they work and so on, then there is a limitation, right? Assuming set, yes.
Is all like specific for quadratic functions, or do you think it can be extended to polynomials or some, you know, differential representation?
So this result, in fact, holds for a polynomial, and if your degree is r, then this becomes r. Yeah, so actually this result, it's a very simple result. It's more like an observation, right? It just follows by the linearization trick, right? Like for example, in SVMs, if you have polynomial kernels, you can lift your points into some, you know, high-dimensional space, and then it's just a linear operation, right? So it's a very similar case here, right? So yeah, so this is not, you know, not a big deal, right? Except that it does show that the activation function matters, right? So. Okay, good. Excellent questions. So I think I still have 5 minutes left, or 2 minutes left. So the remaining few minutes, let me just give you a quick outline of this result. This result actually is fairly straightforward. So it's not immediate, but it's quite straightforward once you have the machinery. So let me just say a few words about this result. So as before, we don't have to start from scratch, right? We don't have to reduce from SAT. Instead, we're going to start from the bichromatic Hamming closed pair problem, right? Which is actually a very interesting problem in itself, right? So here you are given two sets of vectors, binary vectors, and you want to see if there's any pair which is close, right? Whose distance at most t. As of course, there's lots of algorithms for that, you know, lots of sub-quadratic-time algorithms once you allow approximation, right? You know, by Greg, Allman and Williams, localized hashing, and so on. But if you want the exact solution, Quadratic-Time is pretty much the best thing known. So what we are going to do is we are going to take this problem and reduce it to SVM, right? In fact, the same thing can be done for a gradient problem. So how do we do this reduction? Well, we take this problem, and an interesting twist is that unlike most of the other reductions, at least all the reductions in this talk, this reduction is not one-to-one, right? So, you know, previously we mapped one input to one input, right? Here we actually map one input to closed pair to three instances of SVM, one instance only for vectors in one set, another for the vectors in the other set, and the third one for the union, right? And here, these guys have label 1, these guys have label -1, and the same labels here. Okay, so what we do is we solve the set 3 problems, and from the solutions we can detect if there is a close pair or not. So what's the intuition behind it? Well, so let's write those optimization problems, right? So here you have SVM for vectors A, right? Here you have an SVM for vectors B, right? So the only difference is that here labels are -1, so you have some -1s here and there. Right here they cancel out, but they do appear here. And here you have the big SVM for the union of the two, right? So it looks like a mess, but it's actually, as in a moment, it's actually have a pretty clear structure, okay? So suppose that you solve these problems, right? So what this solution tells you about the original closest pair problem. Okay, so we have to be able to distinguish between the yes case and the no case, right, of the closest pair problem. So let's start from the no case, right? So suppose that for all pairs of vectors, the Hamming distance between them is at least t, okay? All right, so what does it mean? Well, if the distance between the vectors is large, that means that the kernel distance, which in our case is a Gaussian kernel, is actually small, right? Especially because we can take this constant to be log square n, right? So if this is large, this value is small. So for all purposes, at least for the purpose of our proof, we can assume it's close to 0, okay? Which means that all the cross terms here disappear, right? So this disappears, this disappears, this disappears, and I think this is all that disappears. Now what is left are the terms which do not involve, expression which do not involve cross terms, right? And you can see what is happening, right? So the expression for the SVM for the union essentially consists of terms inherited from this program, right, in blue, and for this program in orange. Okay, and these terms, these expressions don't interact with each other at all, right? Because all the cross terms are gone, which means that solving this SVM actually gives you a solution which is very close to the sum of the two other solutions, right? So in this case, you actually have the situation that the value of the joint program is almost equal to the sum of the values. Okay. So this is in the no case. Now, in the yes case, you actually have at least one pair, which is with a distance at most t minus 1. Okay. So once you go through the kernel, this means that the kernel value is at least this quantity here, and because it's an exponent and you have a pretty large constant here, or the factor here, this is actually significantly larger than for the case of t, right? There's a big gap here, right? Even bigger than polynomial. So this means that unlike in the previous case, the cross terms actually start to interact, okay? And what you can prove is that what this means is that the value of A union B is actually not the same as the sum of these values, right? So by computing these things and comparing them, you can actually distinguish whether there is a close pair or not, right? And this means that the reduction is correct, okay? Any questions about that? Right? I mean, it's a rough intuition, but it really summarizes the essence of the reduction. All right, so that pretty much concludes the talk, right? So in conclusion, what we have seen is a conditional hardness of a collection of problems for text processing and machine learning. All right, so they kind of provide some sort of a guidelines of what can and what cannot be improved algorithmically in these areas, right? And we also have seen a couple of examples of algorithmic results, right, that happened because of these limitations, right? So the hope is that this methodology, in analogy to NP completeness, can guide algorithmic research, right? Because we do have tools now to figure out when to stop. so to speak. And needless to say, it's a very dynamically developing area. There are many interesting open problems. Perhaps if there is one problem which would be very interesting to understand is what happens for these problems when you actually have approximation, right? Because, for example, for the eddy distance, hardness just holds for the case when you want to distinguish between essentially distance of n and n-1. Right, so it's really a razor-sharp gap. Okay, and doesn't say absolutely anything what happens if you want to find an approximation up to even say 1.1001 or something like that. Right? I mean, for all you know, this could be a linear time solvable problem. We have no evidence that to the contrary. Right? So this is a very interesting question. I mean, there has been a progress on this. So if you restrict your attention to deterministic algorithms, right, so no randomization, then Amir and Arthur show that assuming by making certain assumptions about pseudorandom generators, one can actually get some pretty good lower bounds, right? But like once you allow randomization, I mean, at this point, it's all wide open. And last but not least, it will be very interesting to see, it would be nice to have more happy faces, so to speak, right? So it would be very nice to have algorithmic results, right, which are generated, thanks to those limitation tools. All right, so that concludes my talk. Thanks all for coming. Sure.
So your edit distance lower bound, that lower bound seems very robust to the notion of distance that you use.
Yeah.
So if you disallow deletions, very small lower bound, the same technique should do a lower bound too.
So that's interesting. So it's relatively robust, but it's actually not robust enough to capture all different costs. Right? So for example, if you disallow substitutions, right, but essentially just have insertion and deletions, then it becomes equivalent to the longest common subsequence problem. And actually, just using this technology, at least this proof doesn't apply, right? But there has been two follow-up papers, one by Amir, Virginia, and Artur Bachkurs, and another by Karl Brinkmann and Kuhnemann, right, who showed that, in fact, similar lower bound applies to the longest common subsequence. In fact, the second paper essentially proved a pretty general theorem, right, that as long as you have certain, vector gadgets, so to speak, which exist for many different costs, then the lower bound also applies, right? Yeah, of course, if you disallow insertions and deletions, you have only substitutions, then lower bound doesn't apply, right? Because then the problem actually can be solved in n log n time, right? So, yeah, so it's a pretty general result which characterizes what can be done, what cannot be done. Yeah, yeah. But essentially the trick is in designing those vector gadgets, right? Which I didn't cover, but that's roughly where the technicalities are buried. Yeah. Yes. Leo, yeah?
Maybe 20 years ago, there were a number of papers in geometry showing that certain problems are what was called three-sum hard.
Oh, yes.
These were problems like covering a square by a bunch of triangles, and they were quadratic time.
Yes.
And they showed basically that in this problem, given a set of numbers, there are two numbers whose sum is equal to another number.
Yes.
And they showed that basically, if you could solve that problem faster than n squared,
yes,
you could solve this three-sum problem faster than n squared.
Yes, yes, yes.
Does this fit into this someplace?
So that's a fascinating question. Yeah. So I mentioned that there are several assumptions that you can start from, and three-sum is certainly the oldest. Yeah, it's the oldest of them, right? Because the paper by Overmars and it says like I think in the 90s or something, right? Yeah, yeah. So so there are several different assumptions that one can start from. Now, the relation between, and yes, I mean, there has been lots of success stories in computational geometry, right, which even predates this recent developments. Now, the relation between tree-sum and orthogonal vectors, I mean, it's a very murky, right? So I believe that in general, there is some weak evidence that you cannot reduce, I forgot the direction, tree-sum to orthogonal vectors, or the other way. The other way, right? Yeah, so there is in general, the relationship between these two problems is not known, yes, but you are definitely very much right. There are other assumptions that led to many interesting developments. Tree-sum is one of them. All pairs shortest path in the weighted graph is another, right? So right now there is a collection of these conjecture hard problems one can start from, and the relation between is also a very interesting question, yeah. Yes?
Are you going to speculate publicly on Seth?
Well, you know, sure, yeah. I mean, you know, I don't see any reason why it should be false, in principle. Yeah, so if I was to make a guess, that would be my guess, right? But again, you know, I think that, you know, speculation is the right word, right? So I guess you can pick whatever options you would like. Yeah, I think, you know, there are, I guess, you know, there are some reasons to think that it might be false, right? But if pressed, I would go for the true, yeah.
So you showed these examples where set gives really tight, roughly quadratic bounds for. Are there other natural problems where you get polynomial time with different exponents, like cubic time?
Oh, cubic time? Yeah. Right, so for cubic, I think that all pairs shortest path, am I right? Well, it depends cubic respect to what, right? Because like if you look at graphs, you have number of edges, you have number of vertices, right? So cubic can mean several things. Amir, can you help me?
Sometimes you can get from it, like
yeah.
you have a distance between three sequences and stuff.
Right. So there are natural higher dimensional generalizations of the problems. Right. I mean, so then you can get some cubic lower bounds for problems involving matrices, but then, you know, it's cubic respect to the not respect to the size of the input, but the you know, matrices are n by n, right? So it's really 3/2, right? Yeah. So there are certain examples, but perhaps not that many of them. Yeah. Yes.
I'm really excited by the bounds we have for SVMs and the simple neural nets. I'm curious, like, based on your experience, what other classes of models do you think are most promising for future similar bounds that we can have the potential to like drive them for?
I see.
Like, is there certain classes you think are easier to prove these bounds for than versus others?
Right. Yeah, I mean, this is a very good question. You know, I don't have a candidate right now on top of my head, right? I mean, I can say maybe why, like, what is the reason why quadratic bounds are possible for these two classes, right? So it says in SVM, it's pretty crucial, in kernel SVMs, right? It's actually pretty crucial that essentially the formulation of the problem implicitly assumes some sort of a kernel matrix, right? So you have some sort of pairwise interaction, right? And most likely in any problem or in many problems which involve this so-called pairwise interactions, right? It's quite likely that you could prove a quadratic time, right? So in our paper we showed, I mean, not just for kernel SVMs, but also for kernel PCA, you know, ridge regression and kernel ridge regression and similar problems, right? That this behavior applies. I think now the key assumption in our arguments is that the kernel function is a Gaussian, or to be more precise, it decays very quickly, right? You have a pretty high decay, right? And this is because we wanted to have a large gap, right, between the lifted points, right? Now, I think that similar results should hold for a wider class of kernels, like for example Cauchy, which decay polynomially, but the techniques do not go through as we have right now. But I think the result should still hold. Right, and actually I think that this would be a very interesting question, right? Whether you can generalize this result to a wider class of kernels. And for the neural networks, the reason why this lower bounds hold is that again, we have some sort of there is the way neural networks work. There is a dot product followed by nonlinearities, right? And you can essentially also find this pairwise interaction, this time between the weight vector and the inputs as well, right? So I suspect that other problems which involve some other classifiers, right, which also involves dot products of this type could also be amenable to similar approaches, right? Yeah, I mean this is admittedly vague, but that's the best thing I can conjecture now. Yeah.
Well, let's thank Piotr again.
Thank you.
And there's a reception following the talk.
For SVMs and the simple neural nets. I'm curious, based on your experience, what other classes of models do you think are most promising for future similar bounds that we can have the potential to derive them for?
I see.
Those are the classes you think are easier to prove these bounds for than versus others.
Right. Yeah, I mean this is a very good question. I don't have a candidate right now on top of my head, right? I mean, I can say maybe why, what is the reason why quadratic bounds are possible for these two classes, right? So as in SVM, it's pretty crucial in kernel SVMs, right? It's actually pretty crucial that essentially the formulation of the problem implicitly assumes some sort of a kernel matrix, right? So you have some sort of pairwise interaction, right? And most likely in any problem or in many problems which involve this so-called pairwise interactions, right? It's quite likely that you could prove a quadratic time, right? So in our paper we showed, I mean, not just for kernel SVMs, but also for kernel PCA, ridge regression and kernel ridge regression and similar problems, right? That this behavior applies. I think now the key assumption in our arguments is that the kernel function is a Gaussian, or to be more precise, it decays very quickly, right? You have a pretty high decay, right? And this is because we wanted to have a large gap, right, between the lifted points, right? Now, I think that similar results should hold for a wider class of kernels, like for example Cauchy, which decay polynomially, but the techniques do not go through as we have right now. But I think the result should still hold. Right, and actually I think that this would be a very interesting question, right? Whether you can generalize this result to a wider class of kernels. And for the neural networks, the reason why this lower bounds hold is that again, we have some sort of there is the way neural networks work. There is a dot product followed by nonlinearities, right? And you can essentially also find this pairwise interaction, this time between the weight vector and the inputs as well, right? So I suspect that other problems which involve some other classifiers, right, which also involves dot products of this type could also be amenable to similar approaches. right? Yeah, I mean, this is admittedly vague, but you know, that's the best thing I can conjecture now. Yeah.
Well, let's thank Piotr again.
Thank you.
And there's a reception following the talk.